Okay, thank you very much for the nice introduction. It's great to be here, and hopefully I can explain to you a bit about the background of some of the things I work on and also some of the history behind things I've worked on. So this is just a general talk on mathematics and optimal shape. So in the beginning, I'll mainly be doing historical things connected with the classical isoperimetric problem. And then as we move on, we will move into more modern things and worry about questions like vibrations of membranes, vibrations of strings, membranes, and things like that. Okay. So I'm going to begin with the classical isoperimetric problem, which asks for the shape that encloses the shape of a boundary that encloses the most area for a given length of the boundary. So we want closed curves that don't cross themselves, and then the question is to maximize the area. And, well, if you think about even rectangles, you can see fairly quickly that it's bad to have something that's really not long and narrow because you're using a lot of perimeter just to get length like that, and you can consolidate the area in some sense by going to a square that has the same boundary. You'll get a bigger area there. And the Greeks actually understood that for rectangles. They could, I mean, this is a simple problem for rectangles essentially, and they knew the answer there for sure. But, well, okay, so the Greek mathematicians understood that for rectangles for sure, and presumably they understood a bit more than sort of the common person might have. But it is said by some of the historians that people measured land, say, or sizes of cities or sizes of islands by measuring the length of time it took to walk around the city or the island or the land or whatever. And of course, that is essentially a question of you're trying to measure the size of something, and typically by size, at least today, we would mean area, by doing something about measuring the perimeter, measuring the length of the boundary. And as we see with rectangles and squares and so forth, that's really not a good thing or not a great thing to do unless you already know that, well, it's maybe not such a bad thing to do if you already know that your land or your city or whatever is close to being, well, in the case of rectangles, close to being square, or in the case of a city, maybe close to being circular or perhaps semicircular. But anyway, so the isoperimetric problem certainly figures in some of this historical material. If you think about, say, just questions of measuring land, knowing how much to value land for. And okay, so in I guess 400 AD, so 400 after Christ, Proclus did criticize this this idea that you should measure the size of land or city or whatever by measuring the perimeter. And but well, one reason some of this material comes down to us from history is that there's this historical myth, you might say, that's connected with Queen Dido. So the myth of Queen Dido is that something like, well, maybe 1,000 years before Christ, more or less. So anyway, something on that order, 800, 900 years before Christ. Queen Dido was in what's now Lebanon. And her brother was apparently a very bad guy. Her brother, I guess, killed her father. And then she was in line to be the queen of that area. I think it was the Phoenicians who were living there at that time. At any rate, she was convinced her brother was coming after her next. And so she outfitted a fleet and took the people who were loyal to her and left across the Mediterranean. and wound up landing in North Africa, in what's present-day Tunisia. And so the myth of Queen Dido, which is perhaps a bit more than a myth, I mean, it's in fact recorded by Virgil in the Aeneid, which would have been well after the actual time of Queen Dido, but anyway. But the myth says that she landed in North Africa, and she negotiated with a local chieftain, local chief basically, to that she and her people could have land along the coast that could be enclosed by the hide of an ox. Okay, so this picture, which again is well after the fact, so who knows how accurate this might be, but here's a picture of, I guess this should be Queen Dido, and this is somebody working for her. And what Queen Dido did was she cut this hide of the ox into very thin strips and tied them together end to end. And then in the way that the story is usually told, she got to use the coastline as part of the boundary of the land that she was going to lay off. And so she laid off this hide of the ox that was cut into the thin strips as a semicircle along the coast, and thereby she got way more land than the local people ever thought she was going to get. So they thought they were going to get the better end of the bargain, and she wound up getting the better end of the bargain. And well, again, so, and the fact that she used a semicircle is again saying that she understood something about how best to maximize the area that would be enclosed by this hide of the ox, given that she gets to use the sea coast as a piece of the boundary for free, essentially. She doesn't have to lay a piece of the ox hide along there. Okay, so that's the Queen Dido problem. So this, of course, figures into, I mean, this is the Queen Dido problem aside from the fact that she gets to use the coastline as part of her boundary is essentially the same as the isoparametric problem, the thing I was talking about here with the first slide there about what shape, okay? Essentially, that's because there's a way of taking a problem like this for the full shape and more or less cutting it in half. And if you can solve the one problem, you can solve the other. So for example, if the answer to this problem is a circle, then the answer to Queen Dido's problem should be a semicircle, and so forth. So I'm going to go through that in a bit more detail in just a bit. Let's rotate the batteries. I'm thinking I'm not there. Okay, now we're moving. Okay, so this is a picture of the city that Queen Dido founded. It's Carthage, or Cartago in Spanish. And you can sort of see that, well, this would be much after she settled, presumably, because it's, I think each individual little unit there is a house. But, and then these are maybe fortifications, or maybe that's fortifications. But anyway, you can see that this has sort of a semicircular outline along through here. And that, anyway, this is a picture of Cartago in more recent times, but maybe still 400 or 500 or more years old. Okay, before I get into the mathematics, let me give you a few more pictures. These are, I'm going to show you a couple of pictures of cities from the Middle Ages. This one is Cologne in Germany. And the idea here is to show you that there are many situations in actual practice or in nature, so to speak, where the growth of something takes a circular form. Okay. Now, and here you see that Cologne was growing along the side of a river, and you see that, well, in fact, if we had just a bit more of this picture, you'd see that there's a little bit of a semicircular town on the other side of the river. But it seems that what happened with Cologne is that it mostly grew on this side of the river. The river was a barrier for getting back and forth. So it's natural that sort of what happens on one side is at least somewhat independent of what happens on the other. But you can see that the city more or less grew in a semicircular way. But you know, the reasons for that may not be exactly that somebody was looking to minimize perimeter for a given area or maximize area for a given perimeter, which are equivalent problems. But well, for the city itself, the city planners might have been thinking about things like that when they built this wall, because certainly a wall costs you money, and if you're going to enclose an area with a wall, you just as well try to do it in a way that encloses the most area. But also just the growth of a city, if you think about it, how a city would grow, people presumably don't want to, people sort of want to add on to the central city in sort of as compact a way as possible. And so that more or less is a local phenomenon that would explain why a city should grow in sort of waves, grow out and more or less form a circular, or give you a circular boundary as it grows. So that's Cologne. Let me show you Paris. Here's Paris. In Paris, you see, well, again, you see this river phenomenon, and you see that the one side grew, it looks like grew faster probably than the other side, probably for similar reasons, but that both are growing in a sort of circular or semicircular way. And you can, in this picture, you can even see that there's an inner wall here. If you look at sort of that inner wall, you see a region that's not quite circular, but not doing too bad of approximating a circle. And then if you look at how the city grew with this next wall, you can see that, well, aside from this piece down in here, it's getting even better at looking like a circle, right? Well, and again, probably some of that's explained by the fact that you've got that river and so forth. Now, if you know Paris, what's called the left bank is actually what's in the right here, right? The left bank is over here, I think, right? But anyway, so I guess that's because of people navigating the river, called the left or the right. Anyway.
But maybe the more important thing is they call the prefecture arrondissement. They're like the round, they're like ground actually. So.
And how it grew with the suburbs and stuff going in, yeah. And again, I don't know precisely the dates for this, but there's a great book for this kind of thing, which is where these pictures came from, called The Parsimonious Universe. I'll give the reference to that at the end, but it has these two pictures and maybe a few more things that are related to this, and they probably give the attributions of these pictures there and maybe even tell you the precise dates. Obviously, these wouldn't have been real pictures. They're presumably somebody's representation, maybe a map maker or something, but anyway. Okay, so now let's turn to the mathematical side of things. So as we've sort of observed, there were people in history who more or less guessed the answer to the isoperimetric problem. That is that the Greeks more or less understood in some sense that if you want to maximize the enclosed area for a given perimeter, you should probably use a circle. And Queen Dido, according to the myth of the founding of Carthage, also understood that, the semicircle. The Greeks were also somewhat influenced by the fact that, the usual history that we hear is that people at the time of Columbus didn't even necessarily understand that the Earth was round, but that's even in dispute, right? Columbus probably did understand the Earth was round, but anyway, but what is known is that the Greeks certainly knew the Earth was round, and when they understood that, they saw that as sort of another point underpinning this whole idea that somehow circles are the most perfect plane figures, spheres are the most perfect round, three-dimensional figures, and so forth. But anyway, the Greeks presumably had no doubt that a spherical shape, would enclose the most volume given given surface area, for a given surface area, and so forth, which is the next dimension up from the Quindito problem, okay? And in fact, if you're a mathematician, you can go off and do this in n dimensions and worry about, what, given a certain surface area, certain measure of surface area in n dimensions, how should you enclose the most volume in n dimensions? And that too has the answer that it should be an n-dimensional sphere. Anyway, okay, so that's the story there for isoparametric. And now let me give you some ideas of how one goes about proving that the circle or the disk maximizes area. So the first thing you should think about is this, that if you have a domain, so this goes with the idea of convexity. So a convex domain is one in which if you choose any 2 points of it and draw the line segment between them, you will not leave the domain. So this figure here is convex, whereas something like this is not convex. Here, if you choose P and Q like that and you draw the line segment between them, you will leave the domain, okay? And so the first thing to observe is that if you have a domain or a shape that should be maximizing area for a given perimeter, you don't want to use anything that's non-convex. And here's the sort of general argument, or the picture that clinches that argument. Here you've got a non-convex domain. You could choose your P and Q here and here, say, and then you'd cross that region where you're going outside the domain. But the trick is, or the way to convince yourself that that's bad, among several ways, is to do this flipping argument. You draw this line that just touches at 2 points, that spans that region where the thing is failing to be convex, and you think to flip this part of the boundary into its reflection across that line, and think about the new domain that you get now that includes that green region plus the 2 pieces on either side of that line. That will surely contain more area, but it will have exactly the same perimeter because you've flipped this part of the boundary into that part of the boundary. Okay, so this allows us to concentrate only on convex domains as we go on. Okay, what's the next step? The next step is to in some sense reduce to a semicircle problem. And for that we use the argument that's more or less illustrated in this picture. Suppose you have a domain that is maximized in the enclosed area. For example, this thing that looks sort of like an ellipse. And suppose you go around the boundary from A to a point B that's halfway around the boundary. In other words, half of the perimeter is being used to go from here to here, and half is used on the lower half. Then you can argue that whenever you do that, the piece of area that you cut off by a line between those 2 points should be the same on either side of the line. And the reason for that is that if it weren't the same, then you could flip the side that was bigger. So if this side down here was turning out bigger, you could flip it into the upper part and now replace your domain by what you get by taking this part and that part and forgetting about the stuff over here. And you would have a domain that has a bigger area and the same perimeter again, right? So you can argue that that no matter whenever you cut the boundary into 2 equal pieces and draw the line between the endpoints of those, that the areas that you get will be the same as well, okay? And this essentially allows us to concentrate on half the domain instead of the whole domain. So from here on, we make arguments about semicircles. So what remains for us to more or less show is that the shape that's going to maximize the area enclosed by just this half of the boundary figure, for example, from A to B there, should be a semicircle if you're maximizing the area. So, and the argument, so here we're dealing with a semicircle. These 2 points are the A and B from the previous figure. And now we think in terms of some arbitrary curve. So this is our curve. Based on what we've said already, we can assume it's convex. But now you can think of drawing this figure with this point O up here, just somewhere on the boundary. In fact, part of the argument is going to be that that point can be anywhere on the boundary, and the same argument works. But so suppose O is a fixed point, And you think of these two shaded regions as rigid, made out of rigid material. So think of them as cut out of a piece of wood or cardboard or whatever. But think now that you can let those two pieces, the angle between them can change. So we're going to adjust the angle between them. And you can argue from that. And well, what you want to do now is you want to maximize the sum of these three areas, this piece, that piece, and the triangle. And it's a matter of just geometry to convince yourself that the way to make this triangular piece biggest is to make the angle up there at O a right angle. Because essentially those two sides are not going to change when you do this, changing the angle there. And all you're changing is the angle, and what controls the area will be what that angle is. And 90 degrees makes it largest. So, and of course the other two regions don't change in area. So to maximize the total area of that semicircular type region, you should make that angle a right angle. Okay, but that has to hold for every point on your curve. And so you have to ask yourself, what sort of curve do we get if we, if for every point we put on the boundary up here, like O, we get a right angle when we draw the line segments to the two ends A and B. And you probably remember, or if you studied high school geometry in the last, whatever, 5 years, 10 years, 20 years, you probably remember that that's a property of semicircles. And I claim it's not so difficult to show that there are no other curves with that property. So that property that you'll get a right angle up here when you draw these two line segments characterizes a semicircle. And that's more or less the way Steiner finished this argument. So Steiner was a mathematician in the 1800s who came up with this way of solving the problem, among others. He actually had several proofs of the isoparametric problem, or the solution to the isoparametric problem. But this is one solution, and it ties back to the Quindito problem because, in essence, he reduces the problem to a semicircle problem and shows that the semicircle is the right answer for that. Okay, there's one small defect of his proof, which is that he more or less assumed that a maximizer of area exists. And it was later realized by mathematicians that even that is a question that you might want to, that you might feel the need of proving, right? Again, to the really early people, this was probably obvious that a maximum region should exist. And in essence, it is sort of obvious. But anyway, it required some extra work to fill in that detail. And mathematicians found other problems that looked similar, where that sort of detail was a real problem. Okay, so here are some other examples where nature is optimizing something. For example, this cat. Now this cat doesn't look that cold, but anyway, you might have observed that a cat on a cold winter's night would often curl up into into a ball, or in some sense make itself as spherical as possible. And at least if you take the picture where the cat is trying to conserve heat, this makes perfect sense, because you can show mathematically that if you've got some object that's hotter than its surroundings, then it will radiate heat into its surroundings according to how much surface area is exposed to the lower temperature and so forth. Anyway, so the reason a cat maybe curls up into a ball is at least that in some sense natural selection or something has caused it to realize, or caused caused evolution to have cats as have that as part of their behavior. Might be a reasonable explanation. But okay, so that's that issue. And also you can also imagine that a cat, suppose the cat were lying on an insulator, then that's sort of the hemisphere problem instead of the sphere problem. But I mean, again, if you look at this cat, is it approximating a hemisphere? Is it approximating a sphere? Maybe a hemisphere is reasonable, right? But anyway, but that I'm not going to say more about. Other examples, I mean, if you go to the classical isoparametric problem, where you're trying to maximize the area of one field given a certain perimeter, the answer is a circle. But if you and your neighbor, or you want to make several fields that maximize area and use less fence, you'll quickly learn that circles aren't really a good thing to do because they don't pack together well. And so like bees, this is actually an image of a beehive with in fact little bees growing in each. These are like immature bees growing in each cell. But bees have more or less solved this problem in that the way to make cells of a given volume and use the least material possible is to make sure that they pack together. In other words, they tile. At least if you look at just this cross section this way, right? They give a tiling of the plane, and regular hexagons is the way to go. And again, the Greeks understood some of this and actually said, yeah, these bees are smart. They've figured out how to maximize or minimize the material that they use to form these individual cells, which could contain growing bees or honey or whatever. But anyway, yeah, again, it's probably an issue of evolution, that bees evolved to be able to do this. Here's another example where hexagons show up. Again, it's a packing problem, but with many, many, in this case, soap bubbles. And this is like soap bubbles between two glass layers. And I guess the pictures may be taken on an angle. But if these soap bubbles were all of the same volume, then you would more or less expect that they should, in the cross section, they should look like regular hexagons. And at least you see an approximation to that in this picture. Okay, so, and again, that's sort of caused by yet a new minimum principle. So there's a certain amount of, what's it called? Well, there's energy in the surface tension of the bubble. And because of that, the bubble wants to, I mean, a stretched bubble, unless it's inflated by air pressure, will become flat. And in this case, like if each of these individual cells has the same pressure inside it, then again, the way they should pack together would be as regular hexagons. Anyway, that's another example from nature. Where am I? Okay. No, okay, so that was where I wanted to be. Okay, so now I'm moving on to music and tones and so forth, right? And so I wanted to begin with the one-dimensional setting where you're just considering a string. You could also think of a piano here, but the great thing about all these problems is that while the motion can be quite complex of an individual string, you can always think of it as built up from these very simple fundamental modes. Okay, and so for people who know some mathematics, this is really the origin of Fourier series, Fourier analysis, stuff like that. But for example, for a piano string, there's a mode where the whole string oscillates up and down in unison more or less, except the things closer to the ends, which are tied down. They move less far from their equilibrium position, which is through the center there. But then there's also a mode where when this end of the string is up, that end is down, and vice versa, so the mode goes like that. And then you can imagine also modes like this, or there would be one with three different of these things, and so forth. And you can go on up with all that. And yeah, if you play guitar or see a guitar played, I mean, what someone is doing when they play one of these instruments and hold the string down somewhere is that they're shortening the string and causing the so if the string is capable of producing a tone that goes with that mode, by shortening the string, you get a tone that goes with, say, one of these higher modes, or something in between even, and that will be of higher frequency, so higher pitch. And so, okay, so that's the modes there. But now, so in some sense, strings are very simple. And so there's not a whole lot to be said about strings. Maybe I should just mention that the Pythagoreans, way back in Greek times, began to understand that strings had this nice simple property of you had a fundamental tone and then you had these overtones. And what they observed was that the overtones, the frequencies of the overtones were simple multiples, in fact, integer multiples of the frequency of the fundamental. So this they took as sort of a guiding principle in their philosophy. Here are some interesting drums. Most of you probably, when I say the word drum, think circular drums. But for the purposes of this talk, certainly, I don't want you to think in those terms. I want you to think perhaps we could have an octagonal drum or a square drum or stuff like that. Here's some more drums. Okay, so there's some more drums. These would all be circular, I think. Now here we start getting into the modes of vibration of a circular drum. And this is a picture of a timpani where you spread sand on it and then cause it to vibrate in one of its natural modes. Okay, so these would be the modes that are separating things out into their simplest form, like we did in the string. And what you find is that there's a fundamental mode where the whole membrane goes up and down, all in unison more or less. And in that case, the sand just spreads to the side and you don't see any interesting patterns. But then there's a mode where when that is up, that is also up, and then the other two pieces there would be down, and then those are vibrating up and down in that way. Or there's a mode here where when this central part is up, the ring around it is down, and vice versa, and so forth. So these are showing all different modes of a timpani, or a bunch of the early modes of a timpani, I should say. And the sand is basically collecting at the places where the thing isn't moving. So back in the string analogy, the sand would be collecting at the place where the thing is crossing through zero. Crossing, did I have that? Probably that's hard to get back to. So anyway, so these are showing you some of these early modes of a timpani. Whoops. Okay. The previous slide was showing you a few more of those modes, so I'll skip over that. But you can also do a similar thing with vibrating plates. So a drum you should think of as sort of like even a piece of a balloon that would be stretched over a frame. And the key feature of a drum is that it doesn't really offer resistance to bending. Okay? But if you go to something like a metal plate, that has a certain rigidity to it, so that it behaves differently than just a drum. And in the mathematics, it obeys higher order differential equations. But at any rate, here's a plate. In this example, which the physics department here actually had a display out in front a few weeks ago, where you could observe this. They had the setup for that experiment. But this is a Chladni plate. Again, you sprinkle sand on it, and you start it vibrating based on this support here in the center. In this case, you have the boundary is not constrained in any way. But this is one example of the modes, the nodes of a mode of vibration of this plate. And the interesting story that goes with this is that this guy, Chladni, observed this experimentally, observed that he could get these interesting patterns by vibrating plates sometime in the early 1800s, and he managed to attract the attention of Napoleon. And Napoleon then was so intrigued by this that he said, I'll offer whoever can explain this phenomenon some amount of gold. Okay? So Napoleon offered gold for solving this problem, and Sophie Germain, who's pictured here, was the person who more or less explained this. She developed a theory of elasticity that gave you equations that tell you about how these plates should move, and then she realized that there would be these normal modes associated with that, and that if you could solve those problems, which is itself a difficult problem, then you would fully be able to recover these Chladni figures. Okay, and so here on the next page, I think, here's some more Chladni type figures for plates. So if you start a circular plate vibrating, you can get these various modes. Again, this is taken, in fact, from a book Chladni wrote. Sorry, I'm going the wrong way. In 1809 on acoustics. And I'm not sure of exactly what the conditions here are, and I'm not sure if he's showing every possible mode. But at any rate, some of these early modes, I guess you could go back and try to look at, well, that's a square plate, right? So you can't really compare here. But some of these modes, I suppose that the center of this plate is tied down, for example, via the bolt that's showed in the other picture or something. But anyway, so these are more figures of this kind. And this is the problem that more or less Sophie Germain solved. Though I'm not sure that she got the gold. I've never heard the end of that story for sure. But in those terms, maybe I'm wasting time here, but you might think about how unusual it might be today for somebody like Trump or whoever to start offering gold bars for the solution of a mathematics problem. Okay, so moving on just a bit, you can ask, can you solve the inverse problem? Can you figure out what shape a drum should have, say, by knowing what modes of vibration it can produce? Or, in fact, in physics in the late 1800s, a similar question came up with respect to the spectra that go with atoms of different elements. So people realized that an atom of sulfur or an atom of oxygen or whatever had certain characteristic frequencies that it could produce, and that if you studied the spectrum, you could distinguish sulfur from oxygen or whatever. In fact, people discovered some elements by studying the spectrum of the sun. They discovered elements that were not known on Earth from studying the spectrum of the sun. But at any rate, Arthur Schuster was involved in this, and he's who's pictured here. And there's a nice quote from him on the next page here, where he's basically mentioning how difficult it is to solve such a problem. Like, he was thinking, I think, in terms of trying to understand what was going on inside an atom by understanding these different frequencies of light that the atom could produce. And he's saying basically, you know, if you know the basic problem in a mechanics problem or whatever it is, and it turned out to be quantum mechanics in this case, but if you know a basic problem, you may have a chance of solving the forward problem. You know the setup and then try to determine what frequencies it produces. But to go back the other way, to know the frequencies and then try to divine from that exactly what mechanical object or whatever is producing it, he says that's a really, really hard problem, right? And he basically says he says this is a problem that's going to be very hard to solve. In the meantime, we must welcome with delight even the smallest step in the desired direction. So that's Schuster on sort of atomic theory, spectral theory. Okay, and now I'm going to turn back to drums and stuff. So the previous was more about atoms, at least Schuster was interested in atoms. But Mark Katz, in a famous article from 1966, which he titled, "Can One Hear the Shape of a Drum?" essentially asked this inverse problem about drums. So he's saying, suppose you know exactly all the modes of natural frequency, all the natural frequencies that a given drum can produce. Can you now figure out or tell what the shape of that drum is? Okay, and so this is the beginning of his article. That's the reference and so forth. Okay, so I jumped ahead a bit. But anyway, this question, Katz's question, was answered. So remember, Katz's paper was 1966, so it was answered, what, 26 years later? By these three people. This is David Webb, Carolyn Gordon, and Scott Wolpert. And they found that the answer to Katz's question was negative. In other words, there exist two domains that aren't the same. And the same here means you can't turn one into the other or you can't superimpose one on the other by say, translating or rotating or even reflecting. So these are really two separate domains, and they give exactly the same spectrum. They give all their natural frequencies are precisely the same. So this was done by Gordon Webb Wolpert. Their original example was those things they're holding, which are more complicated, but fairly quickly it was realized that the actual basis of their proof was that you could take 7 objects in this case triangles, that reflect into each other. So in essence, there's one basic triangle here, and then you reflect it out in various ways, and you'll fill out either this figure or that figure. So in both cases, you're using the same basic triangle, but you're reflecting out in different ways. And it was fairly soon discovered that this was more or less at the basis of what the Gordon-Webb-Wolpert example was doing. Here's a little bit more detail. You can, these are the Gordon-Webb-Wolpert examples. And this is telling you a little bit about how you would go from the actual mode of vibration on one to the mode of vibration of the other. Obviously, since these aren't the same domain, you can't just pick up how the one vibrates and bring it over there. But if you cut things up and glue them back together in a reasonable way, according to what those A's, B's, and C's and stuff, you can say how it should go. But here are some pictures of how the vibrations go in these examples. This is showing you the fundamental mode. It's showing you that most of the vibration is happening here and in the other one over there. But again, how those are connected is not so clear. This is showing another mode of vibration. This one has, for example, that piece up, while that's down, that's up, and so forth. And in fact, this is an example where each of those fundamental triangles I was talking about is basically supporting one mode. So the nodal lines here would be exactly the lines that separate this into the triangle. Here's another one, which it's an even higher mode. It's the 15th mode for that picture. And now finally, I want to talk about a problem of Lord Rayleigh. So Rayleigh was active in the latter half of the 1800s. But he asked the following question. He asked, for what drums of the same area, or from which drum of the same area do you get the lowest bass note, the lowest fundamental tone? Okay, and for that problem, it's really connected back to the isoparametric problem. It's very similar, right? In fact, it's called an isoparametric problem of mathematical physics. So this was his problem. In mathematical symbols, we're talking about first eigenvalues of the two drum problems. In other words, omega here would be representing the drum that we start from, and omega star would be the drum that's circular of the same area. And this leads into what's usually called the Rayleigh-Faber-Cron inequality, which is exactly that. And here's Cron with his wife. But he and Faber independently were able to prove this inequality that Rayleigh had conjectured. So Rayleigh conjectured his thing in back like 1876 or so, and these guys made their proofs in the 1920s. So here's at least some idea of how you do it. So let me just talk in terms of pictures. So suppose you have a drum that's of this funny shape. Remember that the fundamental mode of that drum has everything vibrating out of the board at one time and then back into the board and so forth. But you can basically think of that mode as being given by a certain positive function. And you can think about cutting it by various level lines. So in other words, if you think in terms of topographic maps, these would be the lines that give the height, the lines of the same height around a mountain or something, right? So think of this as being the topographic map of a mountain. You can move this picture over to this picture by thinking to take the outer boundary and form it into a circle of the same area. That would be this outer boundary here. And then you can take each of these level lines from over here and form it into a circle and put it over here, concentric with the first circle, okay? And if you do that, from this mountain, you arrive to a new mountain that's totally symmetric, circularly symmetric about the center. And the great thing about this is that the fundamental mode that in some, you have a certain fundamental mode that goes with this, a frequency that goes with this mode of vibration. And once you take that mode of vibration over here in this way, which is known as circular symmetrization, you will arrive to a problem that in some sense gives you a lower natural mode. And so I think it's on my next slide here. So the details mathematically are this, that when you do this rearrangement procedure, you don't change the integral of u squared, or the integral of u or any power of u. But you do change this energy term, which was upstairs in the quotient I had. And so by moving to the circular situation, that moves down. And then this ratio moves down. Okay? And that's in essence saying that because of this symmetrization process, you've allowed the fundamental tone to slip lower. Okay, so that's the Faber-Cron proof. And finally, let me just mention that there are many open problems in this business. In the early 90s, I was involved with solving one problem, so it's no longer open, but this problem is another isoparametric result that says that, that if you look to maximize this quantity, the ratio of the fundamental tone, sorry, the ratio of the second tone to the fundamental, you will always, you cannot do better than by taking a disk, okay? So among drums, if you take other shapes, the ratio of the first two frequencies, the higher to the lower, will be maximized by taking the circular drum. And this actually has a little bit to do, or has something to do with why drums aren't used to carry the melody in music, because drums, for example, this ratio turns out to be around 1.6. So remember, for strings, the ratio of the second to the first was 2 because the second frequency was twice the first. In this case, it's only 1.6. Those frequencies are probably going to interfere with each other a little bit, and drums typically just are not used for what? The melody, I guess, right? And finally, let me say that here are a couple of books that are quite nice that, that would give you some more detail of what I talked about today. And finally, thank you very much for your attention.